Welcome to EFSA's e-learning on uncertainty analysis. I'm Andy Hart, and this is the last of 3 presentations in the course. In the previous presentation, we focused on basic uncertainty analysis. We looked at each of the key steps in a basic analysis, illustrated by examples from EFSA's Pantoea Opinion, and we discussed how it can be adapted to fit within the time available. In this final presentation, we explore some of the options for refined uncertainty analysis, where some uncertainties are assessed separately from others before quantifying overall uncertainty. And we use an example from the Plant Health Panel to show how this can be both feasible and helpful. There are many options for refined uncertainty analysis, but the basic concept is very simple. Here are the key steps of a basic uncertainty analysis. It starts from the beginning of the assessment, and uncertainties are identified throughout the assessment, but their impact is assessed in a single step at the end of the assessment. A refined uncertainty analysis contains the same basic steps plus an extra one, where some of the uncertainties are assessed separately before assessing overall uncertainty. Refined options can be added at any stage if you decide they're helpful. You might decide at the start, when planning the assessment, to use a critical appraisal tool that includes qualitative criteria for evaluating sources of uncertainty. At the same point, you might decide to quantify some sources of uncertainty using data or expert judgment and then combine them by calculation. Or it might become apparent partway through the assessment that it would be useful to assess some uncertainties separately, for example, using sensitivity analysis. Finally, you might carry out a basic uncertainty analysis, but decide at the end that it's helpful to quantify some uncertainties separately before assessing overall uncertainty. In the plant health example we're going to look at, the assessors decided at the start to use a probabilistic model quantifying uncertainty of key parameters, and then added some sensitivity analysis partway through the assessment. So, why might it be helpful to assess some uncertainties separately? Well, in a basic uncertainty analysis, assessors quantify the combined impact of all the uncertainties on the conclusion by expert judgment. This requires thinking about their individual contributions and how they combine in a single step, which may be difficult. Assessing some uncertainties separately is likely to be easier and more reliable. This is partly because different expertise may be needed for uncertainties affecting different parts of the same assessment. So assessing them separately allows each part to be assessed by the relevant experts. Also, when suitable data are available, part of the uncertainty affecting them can be quantified by statistical analysis. Furthermore, combining uncertainties by calculation is more reliable and transparent than combining them by expert judgment. Of course, refined options require more work and more time, increase the complexity of the assessment, and may require specialist support. So it's important to weigh the costs and benefits when deciding whether to do a refined uncertainty analysis, how many uncertainties to assess separately, and what methods to use. Let's take a look at our example from EFSA's Plant Health Panel. It's an assessment of Pantoea stewartii. EFSA assessed the number of maize seedlings grown from seed imported from the USA that are infected by the bacterium, and they called that N-inf. The panel used a pathway model for 9 factors that influence N-inf. The volume of trade in tons, the average weight of a seed in grams, the prevalence of Stewart's wilt in US maize fields, and 6 factors that reduce the proportion of infected EU seedlings. Here are descriptions of the 6 factors in case you would like to look at them later. Note that they are all proportions between 0 and 1. The panel could have opted to assess an inf and its uncertainty directly by expert judgment based on the available evidence without using a model. This would be a basic uncertainty analysis, and that is what they do in the majority of plant health assessments. For Pantoea, the panel decided to model ninf, assessing uncertainty in 8 of the 9 parameters separately, and then calculating their combined impact using the model for ninf, a refined uncertainty analysis. Methods for assessing uncertainties separately can be qualitative or quantitative. Quantitative methods should be used for assessing overall uncertainty, but qualitative methods can be useful for individual uncertainties. They help prioritize uncertainties for quantification or research and help experts make quantitative judgments of the overall uncertainty. Options for qualitative evaluation include criteria used in evidence appraisal methods, such as critical appraisal tools, verbal expressions, such as high, medium, or low, scores, for example 1, 2, 3, or symbols, such as plus, minus, 2 pluses, and so on, which can indicate the magnitude of uncertainty as well as the direction of its impact on the conclusion. In the Pantoea example, the panel chose to assess uncertainty quantitatively for the 8 parameters in their pathway model. Additional uncertainties were described qualitatively in the opinion. For example, uncertainty about whether papers related to Stewart's wilt refer to sweet corn varieties or maize. Other EFSA opinions have used critical appraisal tools to provide a qualitative evaluation of uncertainties in the evidence. Here's an example from the sodium opinion, which I showed in the previous presentation. The ratings and color coding provide a qualitative measure of the magnitude of different types of uncertainty for each study, which are a helpful input when making quantitative judgments. Now let's look at the options for quantifying sources of uncertainty. The guidance recommends using probability to quantify uncertainty because it has defined meaning and avoids the ambiguity of qualitative expression, as I explained in the first presentation. Probability has an additional advantage when assessing uncertainties separately. It allows them to be combined by calculation. If a parameter in your assessment is binary, has only 2 possible values, then you can quantify its uncertainty with a single probability. For parameters with more than 2 possible values, uncertainty can be quantified by a probability distribution, which quantifies both the range and probabilities of possible values for an uncertain quantity, or a probability bound, which quantifies the probability that the true value lies in a specified range, as I explained in the previous presentation. When suitable data are available, a probability distribution can be obtained by classical statistics, bootstrapping, or Bayesian inference. This quantifies only part of the uncertainty affecting the parameter in question. Other uncertainties affecting the data and assumptions made in the analysis must be considered later when assessing overall uncertainty. Sensitivity analysis involves repeating calculations with alternative inputs to see their effect on the output. This quantifies the range of possible values but not their probabilities, so it doesn't give you a distribution. But it is very helpful for informing expert judgment of overall uncertainty. A probability distribution can be obtained by expert knowledge elicitation, or e.g.P. This quantifies both the range and probability of values and can take account of all identified uncertainties affecting that parameter. A probability bound can also be obtained by e.g.P. This requires fewer judgments but provides less information. All these methods are described in the opinion that accompanies the uncertainty guidance, and specialist support for using them is available within EFSA. In the Pantoea example, semi-formal expert knowledge elicitation was used to quantify uncertainty for the 8 parameters in the pathway model. For example, P1, the proportion of infected mother plants in the USA. The working group experts were asked to assess their lower and upper plausible bounds for this parameter, their median estimate, and quartiles. Then a distribution was fitted to their 5 judgments, as shown by the red curve, for use in the model. The evidence and reasoning for the judgments is reported in the opinion. This process was repeated for all 8 parameters in the model. The panel did not quantify variation in contamination between consignments in the model, but did a separate sensitivity analysis to explore the importance of this additional source of uncertainty. The options for combining uncertainties depend on how they were assessed individually. If they were assessed qualitatively, their combined impact should be quantified by expert judgment, because calculations on scores have no defined meaning. Probability distributions are most commonly combined by Monte Carlo simulation, although other options exist. Probability bounds can be combined by probability bounds analysis, which requires only simple arithmetic. And probabilities for yes-no questions can be combined by a logic model. All these methods are described in the opinion that accompanies the uncertainty guidance, and specialist support for them is available within EFSA. In the Pantoea example, Monte Carlo simulation was used to combine the uncertain parameters in the pathway model. Here is the model that we saw earlier, and here are the distributions elicited by the working group to quantify uncertainty for the 8 parameters. The Monte Carlo simulation repeated the model calculation 10,000 times. In each repetition, one value was sampled at random from each distribution, and the equation was used to calculate one value for the output n-inf. When all the repetitions are complete, you have 10,000 values for n-inf, and these form a distribution quantifying the uncertainty of n-inf. EFSA has developed a user-friendly software tool to carry out these calculations for plant health assessments, and provided training so that all the panel members and staff can use it. When combining uncertainties, it is essential always to consider whether there are any dependencies between them, because this can significantly increase or decrease the combined uncertainty. 2 sources of uncertainty are dependent if assessors think that learning more about one of them would alter their uncertainty about the other one. For example, if you discovered the true value of the prevalence in the USA was here, it might change your distribution for the efficacy of seed sampling in the USA. If you can quantify dependencies from data or expert judgment, you can include them in Monte Carlo simulations. Alternatively, probability bounds analysis allows for any degree of dependence, but gives very conservative results if applied to many parameters. Specialist support for those methods is available in EFSA. Otherwise, the possible impact of dependencies must be taken into account by expert judgment when assessing overall uncertainty. In the Pantoea example, the Monte Carlo simulation assumed that the distributions for the input parameters are independent, so any uncertainty about this assumption should therefore be considered when interpreting the results of the simulation and assessing overall uncertainty. The final step of every uncertainty analysis is assessing overall uncertainty. This is always necessary because no matter how many uncertainties have been quantified earlier in the assessment, there will always be some that are not. In the Pantoea example, there could be uncertainty about the influence of factors that were not included in the model, such as P4, the impact of the semi-formal method used to elicit the distributions, or the assumption that the distributions are independent. When some uncertainties have been quantified separately, assessing overall uncertainty requires combining the result of that with additional uncertainties that have been assessed qualitatively, for example using critical appraisal tools, or only listed. This always requires expert judgment, which can be done using the e.g.P methods in the previous presentation. The Pantoea opinion does not include an assessment of overall uncertainty, as it was done before implementation of the guidance was complete. So let's have a look at an example from the Campylobacter opinion, which we looked at in the previous presentation. The panel used a model based on experimental data to estimate the effectiveness of two control options, vaccination and feed additives, which quantified some of the uncertainties involved. The panel also identified a number of additional uncertainties, including extrapolation from experimental to field conditions. These were combined by expert judgment to assess the overall uncertainty for those two control options. It's important to emphasize that assessment of overall uncertainty is always required, whatever methods have been used to address uncertainty earlier in the assessment. In a basic uncertainty analysis, such as we discussed in the first presentation, the uncertainties are simply listed or described, and the overall uncertainty is assessed by expert judgment. If some uncertainties have been evaluated qualitatively, for example using critical appraisal tools, then the results of that feed into the overall uncertainty assessment together with the other listed uncertainties. And if some uncertainties have been quantified separately, then the results of that also feed into the overall uncertainty assessment, as in the example on the previous slide. Combining uncertainties by expert judgment is a challenging task. To make it easier, you have the option to break it into parts. First, you divide the list of uncertainties into groups that are easier to assess. For example, you might separate uncertainties relating to hazard and exposure, as they require different expertise. Then, quantify the uncertainty for each group and combine the groups by calculation to assess overall uncertainty. Probability bounds analysis might be an attractive option for this in some assessments, as it does not require Monte Carlo simulations nor consideration of dependencies, and won't generate excessive conservatism if the number of parts is small. Dividing the overall uncertainty assessment into parts involves extra work, but should give more reliable results. These options are described in section 16 of the uncertainty guidance, and specialist support is available within EFSA. You can see an example in the 2019 EFSA reports on cumulative risk assessment for pesticides, where the overall uncertainty assessment is divided into two parts, one for uncertainties relating to exposure and one for uncertainties in hazard assessment. After assessing overall uncertainty, we come to the final steps, reporting and communication. Here's a reminder of what I said about reporting in the previous presentation. Report the methods and results of the uncertainty analysis in the same way as other parts of the assessment. Report each conclusion with your quantitative expression of its overall uncertainty, and describe any sources of uncertainty you were unable to include in the quantitative expression and state what assumptions were made about them. In the Pantoea example, the panel omitted parameter P4 from the pathway model, which effectively set it to 0. This means that the results are conditional on assuming that P4 is 0, i.e. assuming there is no testing for Pantoea at the EU border. This should be made clear in reporting and communication. Lastly, if legislation or risk managers require firm conclusions, define the level of certainty required for them. Before we finish, I must tell you a little bit about another EFSA guidance document that you will need when conducting uncertainty analysis, EFSA's guidance on communicating uncertainty. This was published very recently, so some of its recommendations were not yet applied in the examples I showed earlier in the course. It provides guidance for assessors and for EFSA's communication specialists. For assessors, it reiterates the need to quantify overall uncertainty while recognizing that in some cases the final output needs to be a firm conclusion. Assessors are advised to express estimates of incidence or prevalence as frequencies, e.g. 10 seeds per million, and use probability to quantify the uncertainty of the estimate. When assessors quantify uncertainty using probability, communicators are advised to present the probability as percentage certainty for the more probable outcome and not convert the numbers to words. It's also recommended to include a clear and concise summary of the outcome of the uncertainty analysis in the abstract. An example of the last 3 points is provided by the Plant Health Panel's opinion on Robinia, where the abstract ends with this conclusion. Therefore, the panel is 95% sure that 9,950 or more plants per 10,000 will be free from these 2 pests. Detailed specific guidance is provided for communicating different types of output from uncertainty analysis, that is, probabilities, distributions, probability bounds, and so on. So I strongly recommend that you read and apply the guidance on communicating uncertainty together with the guidance on uncertainty analysis. I'll end with an overall summary and some key principles. Presentation 1 provided an introduction to uncertainty analysis, distinguished between basic and refined options, and illustrated basic uncertainty analysis with an example on African swine fever. Presentation 2 explored the methods and options for basic uncertainty analysis in more detail, illustrated by an example on Campylobacter. And Presentation 3 introduced some of the options for refined uncertainty analysis, illustrated by the example on Pantoea. Running through the presentations were a lot of important principles, some of which are shown on this slide. I won't read them again, except to remind you that specialist support for all these methods is available within EFSA when you need it. Thank you for your attention, and I hope what we've covered will be helpful in your work.